That was.
No, very laggy today.
Oh, there it goes. Computer looked like it was having.
It is constantly.
Would it be better to like time for this?
So again, as far as the notes go, if I were you, I would just kind of mostly sit and listen. I might sketch some stuff if I feel like we're working through something, but I wouldn't worry about taking like verbatim notes. All these PowerPoints are on PowerSchool. If you want them, you can certainly print the slides or download the PowerPoints and look at them again when you're doing the homework or whatever. But there's a lot of images. This is why I'm doing this with PowerPoint, because it's hard to draw a three-dimensional figure. And it's especially if you need to draw it a little bit accurately to get a good picture to illustrate what it is that we're doing, which is why I'm doing this digitally. So in particular, I think this is one where if you're not a neat writer and, you know, like good at kind of drawing figures in perspective, this is maybe one that's better to just kind of like sit and listen than it is necessarily to try to copy. Okay?
Wait, so did you say not to take notes?
I think you can probably just sit and listen. You can kind of look at what we're doing, but a lot of it's going to be talking about these figures and like identifying triangles inside of them. So it's going to be like a lot of drawing if you're trying to keep up, which if you're trying to do it fast is not real easy.
So we're not going to have to draw on the
You had me at sit
No.
and listen.
You will not have to draw. For me to explain what's going on, I need to draw and talk about things. But so the first thing I want to talk about is finding the length of a line within a three-dimensional solid. Okay. So when we're doing this, what we're going to need to find is called a calculation triangle. So we're going to find a triangle embedded inside of our three-dimensional figure, and we're going to use that triangle to find the side length or the distance that we're looking for. So what do I mean by a calculation triangle? So inside of a right pyramid, this is one example of a calculation triangle. When I draw these calculation triangles, I am going to be looking for right triangles in particular. Why are right triangles going to be of a special use to us? Because they have a 90-degree angle, which allows us to use what? Two very powerful tools. You can use the Pythagorean theorem, and you can do SOHCAHTOA. Okay, so those are going to be two of our more powerful tools that we're going to use to kind of find these side lengths. Does everybody see the triangle that I have embedded inside of this right pyramid? And then oftentimes on my sheet of paper, this is what I would end up drawing on the side. Rather than trying to draw numbers inside of this, it's a little bit hard to do that. But you need a little bit of like visual imagination to see these things in 3 dimensions. Okay? So there's obvious right triangles, and then there's going to be some unexpected ones. So EDA isn't easy to see that that's going to be a right triangle, right? Because it's just half of one of these rectangles on the side. This triangle FGD, harder to see that that is there and that it's going to be a right triangle. Now it is, because this side GD is the diagonal of this face, and I know that FG is part of this face on the back side of the box. And I know the faces of a box intersect at a 90-degree angle. So this angle here, FGD, is a right angle. It just maybe not easy to see that right away if somebody hasn't pointed those things out to you. So this tends to be the hardest part about this chapter, is the ability to kind of see the right triangle that you need inside of one of these figures, and then get it off to the side onto the sheet of paper with the correct measurements on it. Usually doing the calculation itself is not terribly difficult. getting the correct triangle that you need with the correct measurements on it is usually the hard part for students. But it's not even, when I say hard, it's not nearly as hard as the things that we just got done finished or just finished with. Okay? So much easier than what we just finished. Is everybody okay with this idea? And now you can see why I've told you, probably don't need to try to take notes on this, because this is difficult to do on a sheet of paper, right? Seeing the picture with the colors and the images, and much easier to see what's going on. So let's look at some other unexpected right triangles. So here's a triangular prism. Again, this one, the pink one, should be easy to see because, again, it's just half of one of these rectangular faces. But we have this triangle that runs down the middle of my prism, where again, we know that these faces all meet at 90-degree angles. So this angle EBG is a right angle, but this side GE goes from the midpoint of the base of this triangle all the way up to the corner of the triangle on the opposite side. Can we kind of see that? And again, both of these are right triangles. So right now what I'm trying to do is just build up a little bit of intuition. So like when you see a figure, you're like, okay, where are the right triangles inside of this figure? So the easy ones to find should be the ones that are on the faces, right? If you have a rectangular face, any diagonal you draw on that rectangular face is going to give you a right triangle. The ones on the interior like that, though, like the blue triangle here, are the ones that are usually harder to see, which is why I wanted to go through and do this and draw some pictures and let you guys get a little bit of intuition. Okay? So here's some more. Here are both of these triangles, the pink one and the blue one, are both interior. So here the side EF is the height of this pyramid because it's going from the apex to the base. And then if I take straight perpendicular or at a right angle, you're going to hit the midpoint of this other side. Or also at a right angle, if I go down from the base and I go to one of the corners of the base, that'll also give me a right triangle. So both of those are examples of triangles on the interior. These are the ones that are typically a little bit harder to see right away. But having gone through this, at least you know to help look for those, right? In general, if you have a triangle whose side length is a height and the other side is on the surface of the base, those should be at right angles, because we know that most of these figures that we're drawing are right figures. The height is perpendicular to the base. So let's look at an example now that we've seen kind of where these interior or some of these calculation triangles lie inside of these figures. Let's look at some specific examples. So let's say we have a shoebox that's 32 centimeters long, 18 centimeters wide, and 11 centimeters high. And we want to find the length of the longest rod that will fit inside the box. So we have some kind of a box. Explain to me where I would place the longest rod possible. How would I set that in there? So you got to go from the upper top corner to the lower bottom corner is going to be the longest possible rod that can fit in there. Does everybody agree with that? So you have to think a little bit in 3 dimensions. Use your imagination. Think about this in space. Okay? So we'll sketch ourselves a picture. We'll find our calculation triangle. We'll sketch and label that triangle off to the side and then solve the missing piece that we're looking for from that triangle. Everybody okay with that plan? So here's our box. There's a sketch of it. And then our longest rod is going to go from the upper top to the opposite corner on the bottom. Everybody agree with that? So the triangle I'm going to form with that is this pink one. Can we see that now? Okay. So this side AC is a diagonal for the bottom. Can we see that? The side AG is the length of our rod, and GC is just the height of the box. And now there's a couple of different places we could have drawn this triangle, right? There's 4 options of how we could have drawn this to still get the same answer, right? You could have drawn AG, FD, EC, etc., right? You kind of get the idea. Okay. So if we look at this triangle right now, ACG, we know the side CG, and we know it's a right triangle, but we don't have a third side to this. Or I'm sorry, a second side to this, right? We're also going to need to find the side AC before we can use the Pythagorean theorem to solve the side AG. Can you guys see that? So we're going to need a second calculation triangle to solve AC. Does anybody see what that second calculation triangle that we could use would be?
So, right.
To solve for the side AC. So AC is here. We don't know how long that is. Do you see another triangle that we could use that we know 2 sides of that also includes that side AC? ACD. So this triangle right here is also a right triangle, and we know AD and we know DC, so that would work. So that's what we used. How can we find the length of AC? Pythagorean theorem. 32 squared plus 18 squared, square rooted. So that gives me the square root of 1348. Is okay there?
Mm-hmm.
And now I have enough to solve for that triangle ACG. So there's my triangle ACG. This is just the decimal approximation of the square root of, for AC. And how am I going to solve for AG? Pythagorean theorem again. So when I do that, I get about 38.33. Is everybody okay there? So this is kind of what the problems in this section are going to look like. Okay. In a problem like this, we would have included the picture of the box. I probably wouldn't have had the reference or the calculation triangle embedded in there already for you. You might have had to find that yourself. But notice that there's nothing tremendously complicated about the calculations we're doing. The hard part is finding the triangle that you need and getting the measurements on there correct from the picture, right? That tends to be the hard part for students. Is everybody still doing okay? Let's do another example. So we have the shape EABCD. That's a square-based right pyramid where the sides of the square are 12 centimeters and the height of the pyramid is 95 centimeters. We're going to calculate the length of EC, and then where M is a midpoint of one of the sides, we're going to find the length of EM and the length of EC and explain why it's not the same as EM. Okay, so we're asking you to do several things here. We have a picture coming. If you're curious, it's coming. So here's our picture. Notice that I've already drawn in a calculation triangle for us. If we're looking for EC, that's that side. So the triangle that I've drawn, here is this one in pink, EFC. Notice that we know the length for EF. We're looking for the length of EC. Do we know the length of FC? Do we know the length of FC? No. So what are we going to need to do? We're going to need to use another calculation triangle to find the length for FC. Very good. What calculation triangle do we want to use? Let's see. EDC is not a right triangle, though. So you need FC to be a side on your triangle, right? The triangle that you're looking for. FCB, you said? B. Do we know that's a right triangle? I don't think we do. What I would do is I would look at the triangle FCM, where M is the midpoint of this side CD. Or you could think, I guess you'd think about it this way. This is what I did, I guess, in my picture. Is I did the triangle ACD. And again, if this is a right figure, F is the midpoint of this side AC. So I can just find my answer for AC and divide it by 2. Or you could have done what I started to say initially here, with the midpoint there. Either'd be okay. Are we okay there?
Yes.
Now we have enough to find our side EC. Does that feel okay? Okay. Now it says, remember, M is marked halfway along one side of the base. So here's me drawing M in. And we want the length of EM. So again, I've shaded in a calculation triangle for us. So we know EF, that was given to us, right? That's just the height of the pyramid. We're looking for EM, but we don't know what FM is. But we can find that, and we don't even need a calculation triangle to do it. What is the length of FM going to be?
6.
It is going to be 6. How did you get 6, Caleb?
Because the sides are 12.
The sides are 12. And F is like the center of that base. It's got to be 6 and then 6 to give us 12 total. Good. Everybody feel okay on that? So here's our calculation triangle. We use the Pythagorean theorem and we get 11.24. Notice that this is not the same answer as we got for EC. Go ahead and look here at these two reference triangles or calculation triangles we've drawn. EC and EM are definitely different segments, right? Which one should be bigger? Should be EM, because if I look at the triangle ECD, EM would be the height of that triangle, right? So it should be longer than its side length, than any of the side lengths. Everybody agree with that? So vocab here, again, EC is a slant edge. And EM is like the vertical height for this triangle EBC, one of the faces, the triangular faces. Is everybody okay there? And this is a common place that like students get confused as they use the slant edge for the height of one of these triangular faces when we calculate surface areas. So you have to be a little bit careful there. That's why I've included this example, is because that's a common mistake I see students make. We'll do some more examples here. So let's say we have a cone that has a slant, a slant length of 11.3, and the angle at its apex is 53 degrees, and we want to calculate the radius of the cone, which in my picture I've drawn as DC. So I've already drawn in a calculation triangle for us. We'll use this triangle BDC. Everybody's okay there? Okay. So we're solving for side CD, which I've labeled with the variable R here. What else do we know in this triangle? Do we know any other of the side lengths?
Yes.
Yes. What side length do we know? BC is 11.3. It's got to be the same as AB, right? Good. And do we know anything about BD? No, right? We don't have enough information to find anything out about BD. So what are we going to use for our other piece of information that we need in this triangle? We're going to use the angle ABC. Now, is ABC the angle in our triangle? No. What is the relationship between angle ABC and the angle DBC? DBC is half of ABC. Does everybody agree with that? You know the geometry reason why we know it's half? So if I take the triangle ABC, if I think about this as a triangle, what kind of triangle is this? Starts with an I. Isosceles triangle, because the two side lengths are the same length. I know that the height of an isosceles triangle is going to bisect that apex angle. Is everybody okay with that? That's a geometry theorem that you may remember or you may not. It should kind of make some common sense, though. It only is true for an isosceles triangle, though, so be careful there. So that angle bisector is only going to work if you're doing it in an isosceles triangle. Equilateral is also isosceles, right? If all three sides are the same, that's still okay to do. All right, so we have this. So how are we going to find this side R? What? Okay, we're going to use SOHCAHTOA. Specifically, we know the hypotenuse, and we know the opposite side to our angle. So which trig function do we want to use? Sine. So I can say sine 26 is equal to opposite over hypotenuse. And when I solve that equation by multiplying both sides by 11.3, I get 5.04. Okay with that? Okay. That's it for today.
Amazing.